So again, we are talking about finding area specifically today. Okay, using some of our basic geometry area formulas like area of a rectangle, area of a triangle, area of a trapezoid, that kind of stuff. Not super calculus heavy today. It's just the intro of this integral stuff that we're going to talk about. Okay, just like when we talked about finding derivatives, we talked about limits. And limits was kind of the hard way of doing derivatives, right? Similar here, this isn't as hard as limits, but you're going to find a lot of area of things and add them together. There's an easier way to do it. Okay, and I'll show you that eventually, but I want to show you why it is that way first, okay? So we're going to skip this first question because I kind of hate it, actually. Kind of worded kind of funny. And we're going to go to example number 2, okay? No, we are going to do this one, though. Sorry. If you do really want to listen to it, though, there is a QR code here you could scan, and it'll talk about that problem. So example 2, we're given a particle P that is moving in a constant velocity of 2 feet per second. So here's kind of our graph of that velocity on the left side there. And it's asking us what is the total distance the particle traveled from t equals 0 to t equals 2 seconds. Okay? Don't think about this too complex. If you're going at 2 feet per second, I'm going 2 feet per second. I'm at 0 seconds. 1 second, 2 seconds. How far have I traveled if I'm going 2 feet per second?
4 feet.
I've traveled 4 feet, right? I can think about this using what we call, I think, in your science classes, dimensional analysis. Does that sound familiar? 2 feet per second times 2 seconds gives you 4 feet. That is what you call it, right? Yeah. Dimensional analysis? Okay. With a little train tracks action. You did that in Algebra 1 because I taught it last year, so I know you did it at some point in algebra as well. Okay, so if I also look at this picture here, we didn't need the picture to actually answer this question, did we? No. But if I look at this picture, could I use this picture to actually answer this question? Yeah. Yes, because if I look at the area underneath this line, 2 times 2 gives me an area of 4. Yeah, that's a square with dimensions of 2 and 2.
Wait, I think we did this.
Okay. Move on. Next one, again, we've got another kind of diagram here. It's specifically talking about number of downloads per week. And then that's on the y-axis, and on the x-axis are your number of weeks. Okay. It's asking us how many total downloads were purchased during the 10-week period. So if I zoom in and look at this graph here, I can kind of split this graph up into a bunch of different shapes if I look at right underneath it. So like for the first one here, if I split this into a rectangle there, this is technically on this side, my units would be 3 downloads per week. And my units on the x-axis are weeks. So I could times that by 4 weeks, where my weeks units cancel out, and I'm left with how many downloads in the first 4 weeks? 12. So 12 downloads. Okay, but I want to go all the way to 10 weeks. So if I wanted to split this into some more shapes, I could go ahead and split a line at 6 and bring that down, and I could bring this down here at 10. What kind of shapes did I just make there? I made 2 different trapezoids, yes. But could I split this up and make them into triangles and rectangles? Yeah. So if I split those into triangles and rectangles, find the area of all of those, we can add them all together to find how many downloads in 10 weeks we have. So let's go ahead and do that. My area of this triangle here would be 1/2 base times height. So that gives me 2. This rectangle underneath is going to give me 2 times 1, which is also 2. The rectangle to the right there is going to be, 4 times 1, so that's 4. And then my big triangle here is 1/2 my base, which is 4, times my height is 8. So that gives me 16. So now if I want to find out in total how many downloads are there, well, I can just add all those things together. So 12 plus 2 plus 2 plus 4 plus 16. That gives me 36 downloads in 10 weeks. okay? We're finding the area underneath the graph. Okay, now all graphs are not going to be straight lines, correct? We got a lot of graphs that we know that are curved, okay? And in those cases, it's not necessarily as easy or as accurate to find the area underneath as it was when they are straight lines, right? Okay, so we're gonna talk about some approximations today, and then we're gonna talk about how we can find it exactly with some more calculus, okay? Again, we've got this picture over here. It's a particle moving along, a particle Q moves along a straight path with the graph of the velocity at time t shown on the left. I don't know why that looked so weird. But this is the velocity graph here, over here on the left. So if I wanted to find the total distance traveled from 0 to 2, just like I did on the previous page when it was a straight line, horizontal like this, all I had to do was just, multiply my base times my height to give me 4, right? But if I made a rectangle here, is that going to give me the area underneath the curve? Not exactly, right? So what we are going to do is we are going to actually multiply and find the area underneath the curve by using rectangles, okay? So we're going to find the area using rectangles. Because we know that the time, like if we were finding distance is rate times your time, right? And we know the time is how many seconds in this case? 2 seconds. But I don't know what my rate is. My rate is actually changing because it's a curve and it's not exactly horizontal, or it's not, So that's changing. We don't know exactly what that is, okay? So we're going to start by talking about rectangles, which is the Riemann sums. Okay, he's the guy that made it up. And then we're going to talk about trapezoids at the end here. So when we are approximating the area under a curve using rectangles, first question we need to ask ourselves is how many rectangles are we going to use? It's going to tell you how many rectangles. We call those subintervals, okay? And then it asks us, how will we be able to determine the height of each rectangle? There are 3 different options. There is the left endpoint option, the midpoint, or the right endpoint, okay? You might also hear these called LRAM, MRAM, and RRAM, okay? Where the RAM part stands for rectangular approximation method, okay? So it's the left rectangular approximation method, the right approximation method, and then the midpoint rectangular approximation method. So this first example says we're going to use the left Riemann sum, okay, so keyword being left, with one subinterval to approximate the area of this curve, and we're given the formula for the area, or for the actual curve that we're given, from t equals 0 to t equals 2. So I only want one rectangle because it says one subinterval, okay? And I'm going from the left-hand side. So I'm going to start at 0 for where my y value is. So this point right here is going to be the top left of my rectangle. And my width is going to be 2 units. And my height is going to be 1, okay? This would be my left Riemann sum, or this is my left rectangular, or rectangle, I should say, for this curve, okay? Now, if I want to find the area of this rectangle, this one's nice and easy. My area of this rectangle would just be my width, which is 2, times my height is 1. So my area of that rectangle right there is 2. Okay, now, did that do a very great job of actually approximating all of the area underneath that curve?
No.
No, there's still some stuff that's not accounted for, right? Again, that's why this is called an approximation. We can get more approximate, or sorry, we can get closer, I should say, by using more rectangles, okay? So, moving on to the next one. Same picture, but this time we're going to use 2 equal subintervals to approximate the area under the same curve from 0 to 2, okay? So left Riemann sum is still the same, but 2 equal subintervals. So I'm going to zoom in on this picture here. And I'm going to start by drawing my first rectangle. And I start on the left side. So this is the top left point of my rectangle for that first rectangle. My second rectangle is going to start on that curve on the left side of wherever the y value is at 1. And I'm going to draw my rectangle like this. Okay, again, still some area here that's not accounted for, right? Okay, so when I find the area of these two shapes, these two rectangles, I have the area of the rectangle in red. That's an easy one because it's just 1 times 1, so that's 1. How would I find this height right here? How could I find that height?
Plug that value to the equation?
Yeah, plug it into the equation, right? So I'm looking at when my t value is 1, what is my y value? So if I plug this in here, 0.5 times 1 squared plus 1, if I plug that in your calculator,
1.5?
yeah, we get 1.5. Okay, so this point right here is at 1 comma 1.5, and we just found that by plugging it into the formula that you were given. So my area of that rectangle would be plus 1 times 1.5, which is just 1.5. So in total, my area of those two rectangles
2.5.
is 2.5. Okay, so a little bit more accurate than the 2 that we originally had with only 1 rectangle. Now we're a little bit closer with 2.5. Okay, now we call this when there's still stuff that we didn't account for, we call this an under approximation because we did not account for everything that is on or underneath our curve.
I guess that's next to the over approximate.
Yes. Okay, so that's the left Riemann sum. Always starting with the left point. That is your top your top left-hand side of your rectangle when you create it. Okay, example 3, same picture again, except this time we're using a right Riemann sum with 2 equal subintervals. Okay, so if I zoom in here, if I were to draw my rectangles on this graph, I'm starting on the right side. So this time I'm going to start at 1, and I'm going to draw my rectangle with that being my height. So that's my first rectangle. My second rectangle, I'm going to take that point at 2, and that is going to be my height of my second rectangle. Okay, now in this case, just like the last one was an under approximation, this one we're actually accounting for more than we need to, so this one we would call what? An over approximation. Okay, so I can find the area of this as well. So area of my blue rectangle there, we already found that point. Remember that height was at 1.5, so 1 comma 1.5 is that value. So I've got 1 times 1.5 for the area of that rectangle, plus the area of my red rectangle has a width of 1 and a height. This one is a nice point as well of 3. If it was not a nice point, I could plug it back into the formula and find out what that y value would be.
4.5.
Yep, add them together, we get 4.5. So again, it's still an over approximation. However, it is still an approximation of some sort, okay? So we have some sort of an idea. Now this next question, pretty straightforward. If we had a bunch more rectangles in there, what do you think is going to happen?
It'll get closer?
It's going to get closer and closer, right? Like if I imagine drawing the teeniest, tiniest little rectangles here, all the way underneath the curve, it's going to get pretty dang accurate, right? Still not going to be exact, which is what the integral is going to give us, but this is going to be very, very close, okay? So it's going to get closer, getting more accurate.
Yeah, kind of like the fake proof that I did before.
Yeah. Okay. Here's a little history there if you want to learn about, I don't know how to say his name exactly, but Riemann, yes, he's the one that came up with the whole Riemann sums. But Friedrich Bernhard, I guess? Yeah, whatever. German guy. Okay? All right, moving on. What did I do? Oh no. There we go. Okay. Okay. So we've got Tiffany posted a picture of her posing with Sir Isaac from the pop group Sir Isaac and the Newtons on her Instagram at 9 a.m. She's up early. The rate that her followers view this picture is modeled with selected values shown in the table above, where t is equal to 0 is representing 9 a.m., and the rate is measured in people per hour. We're going to use this data in order to approximate the following information, okay? We're going to do a right, a left, and a midpoint Riemann sum with all this information, okay? But first thing I want us to do is to draw what this graph looks like so we can kind of see it visually. And then I'll show you how to just use the table, because most of the time they're going to give you, for these problems, they're only going to give you a table. They're not going to give you the graph, okay? So we need to be able to kind of visualize what does a rectangle left and a right look like if you're just given a table, okay? So let's go ahead and, on the previous page, you probably had a little bit of space there. If you make a little graph, that's where I'm going to make it, just right up above here. So I've got my x-axis is going to be hours. And my y-axis is going to be people per hour. You guys still abbreviate people with PPL? Or is that like a 2010 thing? Yeah? No? Yeah? Okay. Okay, so hours I'm going to go by ones. And then I'm going to go by fives on my people per hour. Okay, and all I'm going to do is I'm just going to go ahead and label all this, all these points that are given to us in the table on our graph so that we can kind of draw some pictures on there and make sense of what's happening. All right, so here's our graph of, at certain points of time, t hours after 9 a.m., how many people had viewed her picture, okay? So if I'm starting, for example, it says use a right Riemann sum with 3 subintervals to approximate the area between 0 and 5, okay? So I'm only looking at this first 4 x values there, from 0 to 5. And I want 3 subintervals, okay? Now, the subintervals do not have to have the same change of x value, okay? We're not going to just say at 1, right, 0 to 1. No, we're given specifically 3 intervals here already, from 0 to 2, from 2 to 4, and from 4 to 5. Okay, we're given those 3 intervals. So those are the 3 intervals we're going to use. We're not like making up our own, okay? So if I were to draw the right-hand Riemann sum on our graph up here, okay, between 0 and 2, I'm going to draw on the right-hand side of 0 and 2. So at 2, that's going to be my height. So this would be my rectangle that I'm finding the area of, okay? Now the area of that rectangle would be the change of x, which is 2, times my height, which is 30.
50.
Okay, which if we look here from our table, we're using this 2 because it's the difference here of 2, and then we're using this y value of 30 because it's the right-hand side, not the left-hand side, okay? If I was doing the left-hand Riemann sum, I would have drawn my rectangle at 41 and then over to make my rectangle, okay? So this interval change here is 2. In between 2 and 4, I'm changing by 2 as well. So I'm going to add the change of x, which is 2, times, let's draw this picture on the graph, at 4, I'm drawing my right-hand Riemann sum using the right point of 2 and 4, which means I'm going to use which height, 30 or 54? 54, okay? So I'm going to times 2 by 54. And then my last interval here between 4 and 5 is only a change of 1. So I'm going to have plus 1 times. If I were to draw my right-hand Riemann sum up here, I would choose 5, make my rectangle. And then my height of that rectangle is going to be what?
26.
26. So times this by 26. I don't know why that just got very large there for some reason, but
94 in total.
26. There we go. Yes, and if I add all those things together, my answer would be 194. But what does it mean in terms of the context of the problem? What is it? 194 people per hour, 194 hours, 194 people? What is it? Yeah, it's 194 people have seen this picture, right? So 194 people viewed the picture in the first 5 hours. Okay, reason for that is because technically we're taking hours and we're multiplying it by people per hour. So those units are going away and we're just left with people. Okay, so that is my right-hand Riemann sum. Next one we're going to do is the left Riemann sum. Left Riemann sum with 4 subintervals between 4 and 12. Okay, so if I zoom in on my table here, I'm looking at from 4 to 12, not the entire 0 to 12, but 4 to 12, and I want 4 subintervals, okay, which means I could go in between 4 and 5, 5 and 6, 6 and 9, and 9 and 12. Those are my 4 subintervals. So I'm going to have 4 rectangles. And now the difference here is the right-hand Riemann sum, we kind of ignored this first number, right, of 0 and 41. We didn't use that 41 height value. For the left-hand Riemann sum, I'm not going to use the last y value. I'm only going to use the first 4, okay? Because if I drew this on the graph, I'm going to kind of use a highlighter here. My left-hand Riemann sum between 4 and 5 would be, here is my 4 value, to 5 would look something like this for my left-hand Riemann sum between 4 and 5. Between 5 and 6, I would choose 5 as my starting point and then create my left-hand Riemann sum, or my right rectangle, I should say. Between 6 and 9, I would start at 6 and go all the way over to 9. And then I would go from 9 all the way over to 12. Always choosing the left point for your height value. Okay, so let's write this out in terms of actually like the formula of our rectangles. Okay, the difference between 4 and 5 is just going to be 1. So I've got 1 times my height of my first rectangle is what, 54 or 26?
54.
54 because we're going on the left. Okay. Difference between 5 and 6 is my second rectangle, so that's 1 again. And then if I'm using left, I'm going to use 26. Difference between 6 and 9 is 3, so I've got 3 times. I want to use my left point there, so my height is going to be what for this rectangle?
21.
It's going to be 21. And then my last rectangle, same thing. It's going to also have a width of 3 with a height of 44. Okay, so for left-hand Riemann sum, we ignore the last y value. For right-hand Riemann sum, we ignore the first y value. Okay, so I can add all these things together. When I add all these together and I multiply it out, I get 275. Okay, and again, what does this mean in terms of the problem? 275 what? People. But more specifically, 275 people did what? Viewed the picture between 4 and 12, right? So viewed the pic between 4 and 12 hours after 9 a.m. Okay, so that was left and that was right. Last one is midpoint. Okay, last here is we got the midpoint. Okay, for the same example, we're doing the midpoint Riemann sum with 3 subintervals between 0 and 12. Okay, so if I go back up here to my table, I'm looking at this entire thing from 0 to 12, and I want 3 subintervals. So I'm going to split this into from 0 to 4, from 4 to 6, and from 6 to 12. Okay, again, the change of x of all of those are not going to be the same, but that's what we're given, so we're going to use those sub-intervals because we know what the y value or what the rate is at that point. Okay? Now, all the midpoint says is that I'm going to take, for example, this first rectangle between 0 and 4. I'm going to throw my height at 2. I'm going to use the midpoint height, I should say, to make my rectangle. Okay, so the midpoint between 0 and 4, in this case, is 2. And my height is 30. Okay, so my height being 30, my width is going to actually be what, though, from 0 to 4?
4.
4. Okay, so the area of this first rectangle is 4 times 30. Okay, the next rectangle is from 4 to 6. So from 4 to 6, with my midpoint at 526, I would draw my rectangle. Sorry, it's kind of confusing because they're like all overlaying on each other here. But my midpoint rectangle would look like that. I'm choosing the y value to be at 5. So my height there is 26. What's the width of that rectangle, though, from 4 to 6? 2. Okay, so my rectangle area for this one would be 2 times 26. And then lastly, we're looking from 6 to 12. So from 6 to 12 with my midpoint being at 9, my rectangle would look something like this for my midpoint. So my height would be 44. What is my width going to be for this rectangle?
6.
6. So I've got plus 6 times, oh wait, what was it? 44, thank you. Okay, so you're just taking the midpoint height, and you're still doing the change of x for each of your intervals. So I plug this in my calculator, I add them together, I get 436 people that viewed the picture from 9 a.m. to 9 p.m. Because it's 12 hours after, right? So, all right, now we got trapezoids. If you forgot your formula for a trapezoid, it is right here for you. You take the bases, add them together, divide by 2, and times that by the height. So, trapezoids just allow us another way to approximate things. You'll also see it sometimes as T-ram. Or actually, no, I don't think so, because then it's not rectangular. I could have sworn, though, it does. There's another approximation, like, phrase for it as well. I don't know what it is. But anyways, okay, so we are given y equals sine of x, and we want to approximate the area underneath that curve from 0 to pi with 4 trapezoids, okay? So I'm going to draw a little quick picture here of sine of x.
You should put graphs.
Do we remember what sine of x looks like?
Starts at 1.
It starts at 0. And then if we're going only from 0 to pi, is it going to be above or below the x-axis there? It's above, yes. Looks something like that. Not perfect, but you get the idea, okay? Again, we're only looking at the interval from 0 to pi. If I want to use 4 trapezoids, I need to create 4 sub-intervals here. So I can divide this pi by 4 to get my 4 sub-intervals, right? So I've got 1, 2, 3 tick marks there to give me my 4 intervals. So this would be pi over 4, pi over, well, technically 2 pi over 4, which is pi over 2, right? And then this would be 3 pi over 4. So just add pi over 4 each time, okay? So it's got the same width for each of those trapezoids, or the same height, technically, I should say. Oops, okay. So if I were, let's go ahead and draw, first one will be in blue, okay? So my first trapezoid is gonna start with the point here and a point at pi over 4 on the curve. And then I'm gonna go ahead and connect those two and bring them both down to the x-axis. In this case, it actually looks like a triangle, right? Because it's at 0, 0 technically, right? So if I was to write the formula for this trapezoid, I would have 1/2 times my height. So the distance between those two is going to be pi over 4 for every single one of these. And then I would have the sum of the bases, okay? We're not given all of the y values of these points, but how could I find the y value? Plug it back in. You're given a function here, right? So I can plug it back in. So I'd have sine of 0 is this point right here. And then to find this point at pi over 4, it would be sine of pi over 4. Those are both my y values here, okay? Okay, my next rectangle, let's do red, okay? So I'm going to start at pi over 4 and pi over 2. I'm going to connect those two lines, and then I've got my little rectangle here. And if I were to write the area for this rectangle, or sorry, trapezoid, is 1/2 times pi over 4 again. And then my y value at pi over 4 is sine of pi over 4 plus sine of pi over 2. Next trapezoid is at pi over 2, 3 pi over 2. I can connect those two, make my little rectangle here. Not a rectangle, it's a trapezoid. I keep saying that. Those are trapezoids. And if I wrote my formula here, 1/2 times pi over 4, and then times sine of pi over 4, sorry, pi over 2, plus sine of 3 pi over 2. 3 pi over 4. I really can't talk today, apparently. And then my last trapezoid, starting at 3 pi over 4, ending at pi, I can kind of create basically a triangle here. But I can go ahead and plug it into that formula of sine of 3 pi over 4 plus sine of pi. Okay. Now, these you should technically be able to simplify by hand. However, if I wanted to find actually like the area underneath this curve, and I want to know what all of these things added together equal, to save us some time, I know you guys can use your calculator and add all those things together, but you do get approximately 1.896 as your area underneath the curve from 0 to pi. Okay. Now, in this case right here, in this picture, is the trapezoidal approximation a little bit more accurate there? There's not as much that we didn't account for, right? Yeah, so it's a little bit more accurate. Any questions on how I got any of those numbers? Okay, we've got 3 examples left. Okay, this is the same thing. We're doing trapezoidal approximation, but we're given a table this time. Okay, and it's it wants us to use 6 sub-intervals. So in this time frame from 0 to 12, I want to make 6 subintervals. So I've got from 0 to 2, 2 to 5, 5 to 6, 6 to 9, 9 to 10, 10 to 12. That gives me 6, yes? And now I just need to find the trapezoid of each of these intervals. Okay, so let's think about this. My first trapezoid is from 0 to 2, so that tells me my height, right, of my trapezoid. So I've got 1/2 times 2 times the sum of my bases, which would be 33 and 25. Okay, I'm going to leave the 1/2 outside because we're going to have 1/2 of every single one of our trapezoids, yes? So that way it just is a little bit less writing for us. Okay, my next trapezoid is in between 2 and 5, so what's the change of x there? 3, yes. And then my bases are going to be 25 and 27, okay, of this trapezoid. Okay, next one is in between 5 and 6. My change of height there would be 1, and times my bases of this trapezoid would be 27 and 13. Keep on going. Between 6 and 9, we've got a distance of 3. With my bases being 13 and 21. In between 9 and 10, your height is going to be 1, and then your bases are 21 and 5. And lastly, I've got my height of 2 with my bases of 5 and 9. Okay, add all these things together, multiply all these numbers together, and you get an answer of 234 miles traveled. All right, moving on, quick little AP tip for those of you taking the AP test. Make sure when you are finding these Riemann sums, please actually show your work. Like, don't just give me the answer of 234. Show me how you got it with all this stuff written out. That is a point on the AP test. So if you don't write that, you do miss a point even if you get the correct answer. Okay. And then lastly is the intro into the calculus. The notation that you will start to see a bunch throughout the rest of this semester is the integral. Okay. So we are going to, for these problems, sketch and shade the region whose area is given by this integral, and then we're going to find the area of these shapes. Okay, these are going to be shapes that you can find the area of with your geometry background. Okay, so a few little notes that I want you to write on here is this little squiggly S thing. This is what we call an integral. Okay, this -3, this number on the bottom, is the x value you start at on the x-axis, and the number on the top is where you end on the x-axis. This thing right here, that is your function. So that is your f of x graph that you're going to actually graph in between those 2 points of -3 and 3. Okay, the dx part should look kind of familiar in the sense of like derivatives and things. We'll talk about what that specifically means probably next class. Okay, does anyone have any idea what this looks like on the graph? Kind of. Opposite of a derivative? Well, yes, that's what an integral is. I'm just talking about the highlighted part in green. The square root of 9 minus x squared.
Probably like a bump.
It's kind of like a bump, yeah. Let's think about this. If I set this equal to y, I'm going to show you here. Oops. Y equals the square root of 9 minus x squared. If I were to kind of manipulate this equation a little bit, I think you're going to see a little quicker what actually this looks like. See how I just squared it? And then I got the x's and y's on one side? That's technically a circle, yes? However, we only have the positive square root. We don't have the negative square root. So it's only going to be the top half of the circle. Okay? So it's going to be a little semicircle above the x-axis from -3 to 3 with a radius of 3. Something like that. Okay? Now, what you want to find using our knowledge of geometry is I want to find the area underneath the curve to the x-axis. Okay, well, how do I find the area of a circle?
Just find the area of a circle, triples up 1/2.
Yeah, divided by 1/2, right? So 1/2 times pi r squared, since my radius is 3, I get 9/2 pi, or 4.5 pi. That's the area that's underneath the curve. You just did your first integral without even doing calculus. Questions on this one? Okay, last one, letter B. We're given the integral from -1 to 1 of 1 minus the absolute value of x. Okay? Think back, what does the absolute value of x look like? Absolute value of x is a v, right? So if I had the negative absolute value of x, that would be upside down, right? So I know it's going to be upside down.
Yeah, what's that called again? A caret?
What's it called? Yeah, a caret, yeah. On the calculator, that's what I call that little symbol there. And then this 1 here does what? It's going to shift the graph where?
Up.
Up 1, okay? And I'm only going between -1 and 1. So normally my graph for absolute value of x, that's negative, would be down here. But I'm shifting it up 1, and be careful on your x-axis, y-axis here. Your 1s are actually at a scale of kind of 2 little boxes there. So I'm going up to 1, and then I'm going to create my graph like this, but it's stopping at -1, and it's stopping at +1. Pretend those are straight lines. I've now created what shape? A triangle. Yes. So now I need to find the area underneath that curve to the x-axis. So we can do area of a triangle 1/2 base times height. So this would be a base of 2 with a height of 1.
So what?
Yeah, so my area of this triangle is just 1.